very exciting workshop to bring all the people in the community to London, which is very close to Nottingham. Okay, so I will also add a little bit of diversity as Stu just mentioned. So in this talk, I will focus on Rydberg states for the trapped ions and how we can do with the Rydberg states. So this is a picture from Marcus Henrich's experiment. So this is one of the PhD's experiments. So you see you have a linear string of trapped ions, and then so these ions are in ground state. So what you can do is you can use the laser excitation, which is very similar to the Rydberg atom excitation, like for example, two-photon excitation, and it brings them to the Rydberg state. Now you find that in the Rydberg state, the properties are very similar to neutral atoms. However, because here we have a singly charged ion, that means so. Okay, so I forgot to mention. So here in this experiment, so we use strong-shape ions. Okay, so you have effectively you find that at the ion core, the charge is 2. In neutral atoms, we know that the charge is 1. Okay, then you have the electron, the Rydberg electron, which flies around the at the outermost shell. So here, so we still have the very nice scaling in the Rydberg state, but it will also it will depend on the principal quantum number n, but also depend on the effective charge Z. Since here Z is 2, normally in neutral atoms it once require too much, but here Z is 2. We find that some properties will be modified quite dramatically. For example, the energy now is also proportional to Z to the power of 2. Okay, dipole moment becomes slightly smaller. So roughly, if you have same n, you can say okay, 2 times smaller, and the lifetime is affected quite a lot. In the trapped ions, so typically you can bring neighboring ions a few micrometers from 3 to 5. Of course, you can make it even larger, but that is 3, 5 is typical distance in the experiment. And here now, if you look at the interaction, because the Rydberg atom is interesting, we like their interaction. We want to use their interaction to do something interesting, like a gate. Okay, I think. Maybe I just move. Yeah. Okay, so that's fine. But now what we found is that the van der Waals interaction, the dispersion coefficient for the van der Waals interaction now is still down by this Z. So because Z is 2 here, we say that the van der Waals interaction is 70 times smaller than neutral atoms if we have same n. But the good thing is that the dipole-dipole interaction is slightly smaller, but it's not very small. So here, this is an example of the Rydberg state. So this is a plot of the van der Waals interaction. So we see that at a distance of 3 micrometers, so the interaction is sub-megahertz, which is relatively low. And typically, in the experiment, if the distance is slightly larger, so the van der Waals interaction is a kilohertz and even smaller. But so now here, what we can do, we can still use the dipole-dipole interaction to do something interesting. For example, to do the Rydberg excitation blockage. As you know, Marcus will talk about this later. So this is has been demonstrated by Chi a few years ago. Okay. Not only the interaction is modified, but because we have a trap, so we know that the size of the Rydberg electron is large, so the size typically proportional to n to the power 2, which can be a few hundred nanometer. And in the trap, what we find is, so the vibration, the ions are, when the temperature is low, those ions are vibrate along the Rydberg position. So the vibration distance is typically 10 nanometers roughly. Okay, so typical lengths, typical weights, and which is smaller than the Rydberg electron cloud. As a result, what we found is that for the trapped Rydberg ions, typically you cannot consider it as a point particle. Instead, it is like a composite object. So here in the, because here is a black curve is we're supposed to, to show this is the electric potential to trap the ions. So the electric potential that traps the ions itself also brings very strong electron vibrational coupling. So here, this is the shape of the coupling, and this is a capital letter denote the coordinate of the ions, and the small letter denote the electronic coordinate. And this is strong in the Rydberg states. And just to give you a little bit of detail, so this is some typical image of linear Paul trap. So you have electrodes, electric potential applied in different electrodes. So this will create a trap center. This will create an electric potential which composed of time-dependent part. So this omega is RF field, the RF field frequency, but some time-dependent part. Because the ions are relatively heavy, what we found is that the ions cannot really oscillate at this RF frequency. Instead, so the ions are moving at a relatively slower frequency. So the dynamics of the central mass can be described by harmonic oscillation. So the trap frequency is given by these trap parameters. And now, since we know that the Rydberg electron will couple with the central mass motion, now we have to see how we can treat this term. So if we look at the typical time scales in the system, so the Rydberg electrons, we can define a Kepler frequency which is in the order of tens or 100 gigahertz, and the RF frequency typically from a few tens to 100 megahertz. The central mass motion is in the order of megahertz. So we see that this, this Kepler frequency much larger than anything, and this RF frequency is also larger than the central mass motion. So we can do adiabatic elimination or time average sequentially. So in the end, what we find is that so this electron central mass coupling gives us some additional trapping potential if the ions are being Rydberg. So this additional trapping potential will depend on, here we use the rho. Rho is the polarizability in the Rydberg state. So if we look at the polarizability, we find that it strongly depend on different Rydberg states. Okay, so this is for the for J is 1/2, like NS for NP 1/2. So we find that we only have scalar polarizability. If J is larger than 1/2, we will have also tensor polarizability. So in the experiment, because tensor polarizability means that more electronic states will be coupled. So if we want to have a nice simple models, so what we can do, for example, we can couple, we will try to excite NS and P state, NP 1/2 such that this electric potential, additional electric potential will be relatively simpler. Okay, now with this backward, what we want to do is using these properties, so we can still have the backward interaction and also the additional tracking potential. Benefited by this property, we want to create some conical intersection using a pair of trapped ions. Then I will also show that we can also see some very interesting Rabi model dynamics. Okay, so the conical intersection, Igor yesterday already gave a very nice introduction and motivation why we are looking at the conical intersection. They are useful, they are difficult to probe in real systems. So here what we want to do is to engineer such conical intersection with a pair of trapped ions. So in practice, what we find is that we need some linear vibrational and spin coupling. So what we do is we consider two ions, so the trapped in the XZ plane, and the dynamics is along this two-dimensional plane. We use the laser to first prepare the two ions in the S state, then we try to use a microwave field to couple the ions to neighboring NP 1/2 state. Okay, So now we will consider situations such that we have this either one of the ions are in P, but not two of them are both in P because of the blockage. So in this case, what we find is we can define some pseudo spin operator using this pair basis. Okay, so now we use this state-dependent potential. What we can do is if we have the previous instruction for one ion, so now if we have two ions, so they will have Coulomb interaction. So the Coulomb interaction will change the vibrational structure such that there is a central mass motion and a relative motion. If we use this coordinate, substitute this to the effective potential, what we find is that this already gives us a linear coupling. So this X is the relative motion and this Sx is the pseudo spin operator. So this creates one coupling of one direction. So another coupling comes from the dipole-dipole interaction. So this is a dipole-dipole interaction. What we can do is we choose this microwave parameter such that at some point this dipole interaction is zero at some equilibrium positions, or we can choose the equilibrium position of the ions. And such that this linear part, because there is gradient of potential, the linear part of this interaction potential will couple with the spin states through these spin exchange interactions. Okay, so this is we can do a Taylor expansion, but this is some detail. So eventually, what we have is another linear coupling. Another linear coupling is in the z direction coupled with the Sx operator, and the additional tracking potential because SP have different polarizability, the potential is different, so this will create a coupling between the SZ. So eventually we have a two-dimensional coupling between the spin and the vibration. And for this two-level, kind of like two-level system, we can solve it. We can get the adiabatic potential surface, which will depend on the coupling matrix elements. So now this is some typical situation. If we assume that we tune the trap and the equilibrium position such that the ions exactly sitting at the equilibrium position, we can have a symmetric conical intersection. This means we can tune the conical intersection. And if we do not have this perfect condition, what we find is that the conical intersection is shifted out of the center. And here, if you look at the range, it's typically a nanometer, and the critical tracking oscillating frequency is also in the same order of magnitude. Okay, so now here around the conical intersections, there is interesting geometric fact. So this can be seen from the adiabatic basis. From the original Hamiltonian, we diagonalize, we can get the superposition basis that is that will depend on the so-called mixed angle. So this mixed angle. So there is one half which is very important because if we look at this mixing angle, what we find is that so this is the QX, so there is a linear coordinate of the relative motion. So let's say we start from an angle, geometric angle from here, and we rotate around the conical intersection. So the angle theta changes by. However, if we look at here, this mixing angle is only changing by pi. So like here, so this is the geometric angle, this is the mixing angle. So here I change by 2 pi, here we don't have pi. As a result, so they let me see, I think there is a movie. Okay, so this is a simulation. So if we okay, so if we put the we pack it around one of the minimal, what we find is that due to the geometric effect, so the two wave packet will have destructive interference at the other side of the trap. As a result, so the tunneling from one minimal to the other is strongly suppressed. So this is different if we do not assume, if we assume there is no upper potential surface, then we have a trivial double wave potential. So if we have a wave packet here, so what we find is this rapid oscillation between the two waves. And this is the simulation corresponding to previous movie where you see that oscillation A is suppressed. Okay, so I'll be quick. So the next part of the problem will be quick. So I will introduce that actually this in a similar setting we can have a quantum Weibin model. Quantum model recently in the past 10 years is quite hot and popular research topic because although it is very simple, only very recently people find ways to solve the eigenspectral analytically, partial analytically. And in recent years, actually, there are a lot of experiments using different systems to realize such models. So what we do is we can use the similar setting, but in a different condition. We can create a coupling that couple a pair of interaction spins. So the sigma 1x, sigma 2x are the spin operator of the two ends. And this coupling and this interaction couple with the vibration to the relative corresponding to the bracing mode or the relative motion directly. Okay. So then we find that there are different situations. If we neglect this this coupling, the single spin coupling term, we have a so-called asymmetric case. We just gave a name symmetric case. Then we find that this up spin and down spin, they will couple with each other, and this the symmetric superposition and the anti-symmetric spin of a single up spin, they will not couple with each other. So as a result, we find that the Hamiltonian can be put in a block diagonal form, and so this part is relatively complicated just by this additional term. But this block diagonal essentially recovers the original quantum Rydberg model, which is a little bit trivial. But there is the non-trivial case where if we do not neglect this epsilon term, so we find that in this case, this triplet sector are coupled, and the singlet sector of the spins of the pair of spins are decoupled from this. So we do have a block diagonal, so where in this case is a singlet and a triplet spin sector decouple with each other, and this is the form of H1 and H2 corresponding to the triplet and a singlet sector. So this part can be trivially solved. And this part actually is not so trivial. So we develop a method we can find the eigenenergy of this triplet sector. We normally people call it solvable because we do not need to directly diagonalize the Hamiltonian. So this allows us to give. So this is typically called the Bragg G function in the original Rydberg model. So in order to solve this polynomials, we have to solve two groups of iteration relations corresponding to this CDE and C prime, E prime, and D prime. So they can be solved relatively easily. Just give you a flavor how this G function look like. So these black curves are the G function. As long as this black curve cross with 0, it corresponds to it hit one of the eigenvalues. So this, if we collect all these crossing intersecting between this curve with the x-axis, we can find all the dots. If we compare with the numerical calculation, don't find that these two agree very well. Okay, so then in the symmetric case, actually the dynamics will be trivial. So we find that ground state is there is a super and sub regular transition, but the wave function always symmetric. However, with the asymmetric with epsilon term being, we find that the ground state still can have a super regular transition, but the wave function is completely asymmetric as well. So with that, I want to thank you for your attention and all my speakers. So this is my postdoc summary. And the second part is done by Thomas, and you will see much later. And you also Igor. And Fanna is also doing Rydberg study of calcium ions. So, yeah, that I finished here.
Time for maybe one or two quick questions. Perhaps start. You mentioned this timescale separation of motion and diffraction and so on. Like, how does this fare in the presence of the Bohr-Navier, like the convection?
Intersection happens in even slower times. So I think that includes the approximation in separate different time scales.
In the first part, you mentioned this composite structure of the ion. And maybe it comes back to this connection of this Bohr-Navier approximation. So the composite part means that it's polarizable as well as charged.
Yes.
But not that the electron is moving at a different It's not moving together with the ion, or how do you?
So yes, the electron will move with the center. However, what you find is that if the ion moves slightly, so the electron will feel the change of the electron potential, right? So previously the ion and the electron just close to each other, so they only feel the potential at the center of the but now because the electron will feel the flow of this potential, and as a result, this is like a effective stationary type of potential.
All right, so let's thank Weibin again.